embark on this intellectual journey. And I take the opportunity to welcome once again all of you to this FDP. Thank you.
Thank you, ma'am, for those inspiring words. Next, it's my honor to invite our esteemed principal, Dr. M. Muthukannan, to felicitate our distinguished guests.
Thank you. Thank you for the opportunity. Good evening, everyone present here. It's my honor and a privilege to discuss with you before today's. We have gathered for this AICTE ATAL 6 days online FDP on quantum computing and quantum machine learning for sustainable solutions, a field that is poised to redefine the very fabric of the technology and innovation. As we all know, the quantum computing is no longer just a theoretical concept or a distant dream. It has emerged as one of the most dynamic and rapidly advancing in the field of science and technology. Today, we have a unique opportunity to hear from the leading experts, researchers, and leaders who are at the forefront of this groundbreaking discipline. In this FDP, we will delve into the theory applications and the challenges of quantum computing and achieving the SDG goals. We will explore how the quantum bits or qubits differ fundamentally from the classical bits and how the quantum interference are reshaping our approach to problem solving. More importantly, we will discuss the way in which the quantum computing will transform the industry and the society at the large. I would like to take a moment to express my deepest gratitude to the AICTE ATAL for sponsoring our event and to be the chief guest Dr. A. Pavindan, Senior Director R&D, ERNET, Ministry of Electronics and IT, organizers, speakers, and the participants for making this event possible. Your dedication and hard work have ensured that we are able to engage in these critical conversations about the future technology and innovation. As we move forward, I encourage each one of you to not only learn and observe the knowledge shared by our esteemed speakers, but also to think critically and creatively about the immense potential that lies ahead. The future of quantum computing is not just in the hands of scientists and the engineers, but also the collective imagination and the collaborative efforts of all of us. And I look forward to the enlightening discussion and that will unfold over the course of this event. Thank you for the opportunities and welcome you all.
Thank you, sir. Your presence has truly set a wonderful tone for this program. Now, we have the great pleasure of hearing from our distinguished guest. It is a great honor to introduce our distinguished speaker for today's session, Dr. Pavindan Arumugam. Dr. Arumugam serves as the Senior Director, R&D, and the Scientist Chi at the Education and Research Network, ERNET, India, an autonomous society under the Ministry of Electronics and Information Technology. In this role, he is at the forefront of innovation, overseeing vital R&D projects in cutting-edge fields, including the Internet of Things, cloud computing, and quantum communications. A distinguished member of IEEE, Internet Society, ISOC, and ACM, Dr. Arumugam brings with him a wealth of knowledge and expertise. We are truly privileged to have him here today to share his insights. Please join me in giving a warm welcome to Dr. Pavindan Arumugam.
Thank you very much for the introduction. You are able to hear me? Can you confirm?
Yes, sir.
Thank you. Thank you, Principal KCG Technology, Dr. Muthukannan, and Professor Deepa, Head of Research, Department of Electronics, and all the faculty and research scholars who have joined here and the delegates. Good evening to all of you, and happy to see very good participation. I had earlier participated in KCG organized quantum workshop FDP in the last year, and really it's wonderful that it's a timely event and the quantum mission has just kick-started and it is happening at the right time. So the topic on quantum computing, quantum machine learning for sustainable solution is apt and very timely in terms of the relevance to the Indian National Quantum Computing Mission. I thought for the benefit of the larger participants, I'll touch upon the National Quantum Mission, which is a nationwide initiative kickstarted recently, a few months back. And if you see, the National Quantum Mission initiated with a broader aim to harness quantum technologies in general, and specifically on the communication, cryptography, and also the computing, quantum computing in a larger context. And there are 4 thematic hubs that are already set up. IISc Bangalore are leading the quantum computing hub, and IIT Madras jointly with the CDOT leading the quantum communication hub, and IIT Bombay is leading the quantum sensing and meteorology hub, while IIT Delhi leading the materials and devices hub. There are 4 thematic hubs in key verticals on quantum technologies are already set up and operational just a few months back. So in addition to the 4 hubs, there are also mission coordination cell, which is already set up at IIT Kanpur in their outreach center at Noida, which will actually oversee the overall progress and for effective coordination between the hubs, these 4 hubs, and with the Department of Science and Technology to accomplish whatever the hub's mission and the overall hub activity and the progress of the hub, all that will be monitored by the mission coordination cell, which will be coming under the IIT Kanpur. So these were the major governance structure that has been already set up for the National Quantum Mission. And if you see the overall participation within the NQM, there are about 14 technical groups across 17 states of India and 2 union territories. And these hubs focus on technology innovation, skill development. There will be multiple skill programs that will keep happening under the Quantum Hub. And they also intend to connect with a lot of the startups and the entrepreneur and academia in a hub and spoke model. So it is important that all the faculty and students and research scholars who are connecting in this call should remember that these hubs are set up to facilitate the further research and connectivity to other tier 2 colleges and various startups to initiate newer projects and innovation ideas, right? So people can submit to the hubs the ideas so that they can get funded. And also, in addition to that, there are multiple skill programs for us to learn on the emerging topics. So that is the intent with which this is entirely set up. So the model will have the central hub, and multiple spoke institutions can join this project in going forward. At the national scale, various organizations, as we all know, have undertaken the quantum development. Like CDOT has their own indigenous QKD system, and also they have PQC solutions very well deployed and productized already in the market, right? And they also have quantum secured video IP phones, products of this kind. While Defense Research and Development Organization, DRDO, has they are also into testing out a lot of quantum resilient security schemes already. They are into various security schemes, and SETS, Society for Electronic Transaction Security, coming under the Office of the Principal Scientific Advisor, is also accelerating various activities in the PQC. They are already in both the quantum computing and communication hub. So these were various entities within India, government-funded R&D organization, as well as various industry players are already into quantum initiatives within India. And in terms of the national quantum hubs, they have already invited project proposals from startups. If you see some of the quantum hub calls, they've already initiated call for proposal from startups. So I would urge those who have interest in proposal calls, please look into the quantum hubs for the opportunities. and also the keep looking out for the skill programs which they might be offering on a regular basis, so that learning from various hubs, whether you are interested in quantum materials or machine learning or quantum computing. So the events that will get organized on a regular basis, please look out for it. And I really once again appreciate the organizing team in having this timely event, the faculty development program, and bringing together excellent experts from academia, R&D, and industry. And I definitely hope that the participants will have a great time learning about this emerging technology topic. And I convey my best wishes to all the participants, and thanks again, the KCG Tech, and well done in organizing this event. Thank you very much. Yeah. So able to hear? Yeah. Thank you.
Yes, sir. Thank you so much. Now I invite Dr. Sridatan, sir. Sir, are you online?
Yes, ma'am. Can you hear, ma'am?
Yes, so I invite you to give the vote of thanks
Okay.
for the inaugural session.
Okay. Thank you, ma'am. Good evening to everyone. It is my honor and privilege to deliver the vote of thanks on this momentous occasion, the inauguration of Faculty Development Program on Quantum Computing and Quantum Mechanics, Learning for Sustainable Solution, sponsored by AICTE ATAL Academy. First and foremost, I extend my deepest gratitude to our chairman, Dr. Anand Jacob Burgess, Hindustan Group of Institution, whose visionary leadership continues to guide our institution towards academic excellence. A heartfelt thanks to our director, Dr. Annie Jacob, and Deputy Director, Ernid Burgess, KCG College of Technology, for their strategic foresight and unwavering support in bringing this program to life. Your encouragement has been instrumental in shaping its objective. We are truly grateful to our principal, Dr. Muthukannan M., for his being the driving force behind this initiative. Your dedication to faculty development and quality education is the foundation on which this program stands. We also extend our sincere appreciation to Dean Academics, Dr. G. Prabhakaran, Dean IQAC, Dr. Izzat Edward Kennedy, Research Head, Dr. Deepa Jose, and Head of the Department, Electronics and Communication, Dr. Kavita Balamurgan, for their invaluable support, insightful contributions, and seamless coordination in making the faculty development program a reality. We are deeply grateful to ATAL Academy and AICTE for this sponsorship and continuous commitment to advancing faculty development and academic excellence across institutions. To all our faculty members, participants, and organizing team, thank you for your energy, curiosity, and commitment. This program is not just a series of sessions, it is a shared journey of growth and transformation. As we embark on this week of learning, collaboration, and reflection, let us carry forward the spirit of inquiry and openness that defines true academic progress. Thank you once again, and let the FTP begin with the inspiration and purpose. Thank you all.
Thank you, sir. We are now ready for our first technical session. Please join me in welcoming Dr. Pavendan Arumugam once more, who will be speaking on quantum key distribution.
Sir, can you share the slides, sir? We will just check.
Yeah.
Yes, sir.
Just to see. Tell me once you are able to see my screen.
Sure, sir. Sure, sir.
Is it?
Yes, perfect,
Is
sir.
it coming in
Sir,
full
is
screen?
it in,
Okay.
no, sir. Not in full screen.
Okay. Just a minute. Is it okay now, or?
Sir, this itself
Hello?
is fine. This itself is fine. So can you just go to the next slide just to see if the slides are moving?
Okay. No, is it not seen in full screen? Okay, can you just confirm?
It is not seen in full screen. However, the slide is moving.
Okay, just one sec. No,
Yes,
but
sir. Maybe if you
I'm not
reshare again.
using. Yes, yeah, I'll do that. Yes.
Yeah, yes, sir.
I will do one thing. I'll just do the screen share in full screen. Then I think it should be fine. Is it in full screen now?
Perfect, sir. Now it is
Hello.
in full screen.
Okay. Yeah. Thank you. Thank
Yes,
you,
sir.
Prasadeepa. So I
Yes, sir.
will. Yeah. Thanks for the opportunity to present on the quantum key distribution. I will try to introduce the QKD concept and then various testbed activities that we are part of, and also the worldwide testbed activities that are happening in other countries as well as in India. So I'll try to cover. So the outline of my presentation would be to give an overview of the quantum communication and quantum key distribution, and followed by the quantum key distribution protocols and deployment experience worldwide as well as in India. I'll try to cover in my presentation. That is the overall theme of the presentation. So before I get on to the QKD related work, I just wanted to just highlight who we are and what we do. ERNET stands for Education and Research Network. We are academic domain registrar for all the academic domains. edu.in, res.in, ac.in all gets registered with ERNET. We are part of the Ministry of Electronics and IT. We provide various services like EduRoam and smart classroom services, satellite connectivity services for remote regions of the country, and also collaborative R&D with academic institutions, all the premier academic institutions. And also we have recently signed, happy to share that we have also recently signed a MOU with the KCG Tech. And in terms of the focus area of ERNET India, so we have three verticals within ERNET. We carry out R&D activities on quantum communication. Even though ERNET historically is a company which or an organization which focuses on classical communication, recently we have been carrying out projects on the quantum domain. And on the visible light communication, we have a optical wireless communication testbed jointly with IIIT Delhi and IIT Madras and NSUT. Multiple institutions we have collaborated in setting up this testbed. And we have a joint project with the Indian Institute of Science in carrying out tactile internet project, MIT funded project, where telesurgery or remote surgery kind of use cases can be demonstrated using deterministic network. And we have projects in the Internet of Things, especially for the security domain, like sandbox environment development, where devices can be tested for its functional compliance on various protocol layers of IoT devices. And we do carry out various IPv6 and DNS related research and applications. And on the network communication, as I mentioned, we have a VSAT hub in Bangalore connecting to remote regions of the country, like Andaman Nicobar, Lakshadweep, and northeast part of the country. They are one of the major users of our VSAT network. And we do run Wi-Fi campus network for multiple institutions, premier institutions, and various central universities. We provide campus Wi-Fi network. And we also run smart classrooms and EduRoam service, which is essentially roaming with same Wi-Fi credential across institutions and also across countries. Like this is a global service. So with the same SSID one, the academic users can visit multiple campuses or attend conferences where their Wi-Fi access will become seamless with the same Wi-Fi password. So that is the mandate of this eduroam service, where it is available almost the major countries, and this is available across various education and research networks. And in terms of the smart education and emerging technologies, we do run a lot of the cybersecurity projects for a strategic or more critical infrastructural monitoring. And we are a domain registrar, and we do web hosting for educational institutions, and a lot of the website accessibility project also we carry out. So specifically on R&D, maybe I'll quickly brush upon, considering that this is more like a net introduction. So we participate in the quantum access network, which is a field network that is executed. The more details I will be covering, but just to give a glimpse of the idea. So we are part of the Makan project, which is a metro area quantum access network jointly with IIT Madras, SETS and CTAC, where 14-kilometer fiber link is established between IIT, ERNET, SETS and NIC. These links were both ground fiber, underground fiber, as well as the overhead fiber, connecting 4 different institutions for quantum key distribution. And as I mentioned about the tactile internet for telesurgery kind of use case, where the human operator is on the one side, the tele operation is on the other side, where the network needs to provide low latency and a link with sub 10 milliseconds, sub 20 millisecond latency, so that an operation can be performed over the network, where the remote robot will repeat the action which is performed by the human. So these are quite important for telemedicine kind of application or remote maintenance, where the human expert or the human operator is on the one side, and the actual operation gets performed on the remote, where the network reliability and the latency is a crucial bit. So this was demonstrated between Bangalore and Chennai under this project. And in the visible light communication, we had set up a test bed for hybrid Wi-Fi, where the indoor LED lighting infrastructure becomes the last mile internet connectivity for the users, where when the user migrates from the Wi-Fi, when he sits below the light and he moves away from the light, his connectivity needs to seamlessly migrate so that it doesn't break, the existing network connection doesn't break. So this was demonstrated in this project, and also indigenous Wi-Fi hardware was developed. And the rural connectivity using solar panel as a receiver was also demonstrated as a prototype in a lab environment. And in the IoT sandbox development, it is about device testing for various compliance. There are various IoT devices coming into the Indian market, whether they comply to all the protocol layers of the IoT stack. So that this project essentially validates, and currently it is still under development. Once the sandbox system is available, so the device, any IoT device coming into the Indian market will go through a series of tests, and then the functional compliance or the certification will be mentioned in terms of on what aspects the device is compliant and what aspects it is not compliant, so that there is the device manufacturer addresses the security vulnerability or the non-functional compliance issues before they roll out into the market. And in the other project funded by the Telecom Development Fund, Telecom Technology Development Fund under DOT, this project is led by IIT Madras with so many work packages essentially for optical component development, fiber optic component development from transit connectors and switches and so forth, fiber cables and so forth. So in this, our focus area is on QKD security validity check in a real field network. So this detail I will cover it in the future slides. So this is the background. So as I covered in my the inaugural speech as well. So there are 4 thematic hubs already set up in India under the National Quantum Mission. One is led by IIT Madras on the quantum communication, which is a joint hub by IIT Madras and CDOT. It's known as Samkhya Technologies, and they have the almost all the hubs. They have their own URLs, so you will have more information getting populated as they become more. They become operational. So currently, most of the hubs are getting set up, and a lot of the recruitments are in progress. We can see from their site that they are getting into the operational mode going forward. So we might see in 2025, before end of 2025, we will have more actions happening in these hubs. So quantum communication hub essentially is aiming to establish a long distance QKD network from Bangalore all the way up to Delhi, connecting Bangalore, Chennai, and then Chennai, Hyderabad, Indore, and Indore, Delhi. So this long distance quantum key distribution network, they call it as a KILA. So Macan is a metro area quantum access network within a metro city, whereas the quantum internet with local access, it is a long distance QKD network from Bangalore all the way up to Delhi. So with every 50 kilometers, people have to deploy repeaters, and they will validate for multiple QKD protocols. So there are a lot of component level development, and also there will be a test on satellite QKD development, and post-quantum cryptographic algorithm development. So all are part of the quantum communication hub. And similarly, the quantum computing hub is led by IIC Bangalore. So the primary focus is to develop quantum processing unit, quantum computing system of different qubits, and also by different approaches. Some will be trapped ion based quantum computing system, some will be photonics based. So IISc, IIT Bombay, IIT Delhi. So, but IISc Bangalore is leading the hub, but there are multiple consortium members who will develop the quantum computing elements or quantum computers over the period of next 5 to 6 years towards making indigenous quantum computing system in India. So similarly, quantum material and devices hub is being led by IIT Delhi, which will focus on the quantum material and device technology, which will in turn contribute to some of the quantum communication and computing application. And similarly, quantum sensing and meteorology will be led by IIT Bombay. So depending on your interest, definitely, I think keep following these quantum hub activities for your opportunity to participate, and also the call for proposal, because these quantum hubs are going to be operating in a hub and spoke model. So definitely the researchers, the faculties, including the startups in your own ecosystem, might be interested in some of the calls that will get published in these hubs. So it is, if quantum is your interest, definitely these 4 hubs, one has to follow it closely. Yeah. So with this background, I'll try to now get into the QKD and the quantum communication related overview. So as we all know that the classical communication system works based on binary system. It is essentially we send a stream of bits, zeros and ones, and we can do again computations using these binary digits, and we perform and get the answer. So this is a typical classical system. So compared to the classical system in the quantum, instead of a bit, we work on quantum bit, and the quantum bit essentially we can assume to be taking any position within a sphere. If we consider that block sphere on the right hand side, so the qubit psi can be at any location in the sphere. So mathematically it gets represented in quantum computing as A ket 0 plus B ket 1. So it can be in any location within the sphere. So the 0 representing the complete North Pole and then the 1 representing the complete South Pole. So any other value, so it will be in any location within the sphere. So similarly, the operations of the quantum operations are also can be single qubit operations as well as various 2 qubit operations are also possible in the quantum logic. So essentially, this is a marked difference between a classical system and quantum system, where the quantum levels and can take any value. If you consider them to be on a sphere, then it can take any value in the sphere. So now with that background, if you look at the quantum key distribution and to introduce the QKD, so there are 2 approaches to quantum key distribution. One, to protect our communication channel. There are 2 approaches. One is using the quantum key distribution, other using the post-quantum cryptography. So let me try differentiating, because there are many approaches where people say QKD and PQC. So just to for those who have who are new to this, I just give a glimpse of it so that you appreciate the difference between the 2. So essentially, before we establish a secure tunnel, the key needs to be exchanged between the sender and the receiver. That key exchange in our current classical communication system happens through RSA or public key cryptography. So we generally, if I want to send a key to a receiver Bob, then I encrypt that key with his public key, then the receiver decrypts with his private key and then gets the key. So obviously then whatever key I wanted to exchange with the receiver, that key gets transmitted over the channel. And then once we exchange the key, then we can encrypt, and then using the symmetric key crypto system, we can securely communicate over the channel. This is the classical way of securing the tunnel or securing the communication channel. This is employed in TLS, transport layer security, SSL, HTTPS, VPN, all of our traditional secured communication that is happening today in today's network systems. They all use the RSA algorithm. But in the future quantum systems with various algorithms like Shor algorithm, which can do the prime number factorization in polynomial time. Once they can break this entire RSA crypto system, then the premise with which these fundamental security systems or public key cryptography is built will be broken. So the quantum attacks, once the powerful quantum computers will come into the market, then the public key crypto systems are vulnerable to the quantum attacks. So that is the scenario with which this background with which this QKD and PQC were developed. So the quantum key distribution essentially shares the cryptographic keys between a sender and receiver. Instead of using a classical channel or classical instead of sending this key using a classical channel, it uses a quantum channel for sending the key, so that the sender and receiver safely assume that the key has been received safely by the receiver. That is ensured in the thanks to the quantum mechanics, that any thing that we send it using a quantum channel, the data is safe and secure. Theoretically, this is proven and it is also practically validated. And in the post-quantum cryptography, instead of using a physical properties of quantum mechanics, PQC enables the different approaches. Instead of using a public key crypto system like RSA, it uses a lattice-based cryptography that is secure against the quantum attacks. So it is more algorithmic alternative to RSA for protecting the communication channel. So one is the answer using algorithmic approach, another is using principles of quantum mechanics to protect the quantum channel. So when it comes to PQC, there are multiple recommendations already released by NIST, which is a US standardization body, especially focusing a lot of things on security. They have already released a module lattice-based key encapsulation mechanism using Crystal Kyber. This is already released, and various open source implementations are available. People have validated with the TLS and other protocols in the public domain. This is PQC based. And again, similarly for the key digital signature also, a module lattice-based algorithms, crystals, dilithium is also released. And these standards are also implemented in open source. Similarly, hash-based signature algorithm. Whatever we do with RSA, the equivalent of PQC-based algorithms have already been established, and NIST has given its recommendations already for these algorithms. One can test it out and do research on using open source implementations available, and also follow the recommended specifications and standards as given by NIST if one wants to implement PQC algorithms. Now let us understand why we need this quantum communication. So the quantum communication, if we see, as I mentioned, it ensures that when we send a data from Alice to Bob, even in the presence of a Eve, an attacker in the middle, the data that gets sent from transmitter Alice and a receiver Bob is ensured to safely received. That assurance is given by two aspects of the quantum communication. One is the no cloning theorem. No cloning means if we make copy of the data, or an intruder trying to make copy of the communicated data in the quantum channel, then both the sender and receiver will easily be able to find out, because they are sent as single photons with a particular polarization. So whenever a Eve node is trying to tap into the channel, the Alice and the Bob will get to know, because the data gets lost, and also the polarization will be changing, and the number of the bit error rate will be very high. So definitely the presence of Eve will be detected by both Alice and Bob whenever there is a eavesdropping into the quantum channel. So this no cloning is an important part of the quantum communication, which ensures that nobody can eavesdrop, or whenever there is an eavesdrop, both a sender and receiver gets to know, or they can detect this part. And similarly, the another aspect is the entanglement. Similarly, when the Eve is trying to listen to the channel, then the entanglement between the Alice and Bob will reduce. So that will show again as a quantum bit error rate. So whenever the Q-bar is going to get high, so that means that some eavesdropper is trying to fiddle with the channel. So automatically the Bob and Alice will get to know, and that will also indicate that the presence of Eve. and they either use an alternate path or abandon the communication and restart or at a later time, right? Or use a different fiber to communicate the key. So this is essentially what does it mean? If the key is successfully received by Bob, we can 100% be guaranteed that there is nobody has listened to the channel, nobody is having the copy of that key. So that much guarantee is given in the quantum communication. So that is what is the message here. And let us come back to the quantum key distribution introduction. So having seen the basics of the quantum communication, now what does the quantum key distribution achieve? So the quantum key distribution essentially is a method for sharing the cryptographic key between a sender and receiver. So once the sender and receivers share the keys, then future communication can be secured. Like they can encrypt and then the receiver can decrypt using the same key. So the current systems, as we have seen it in the previous slides, like they use RSA algorithm for sharing the key, which is prone to quantum attack. For example, somebody knowing the public key using a Shor algorithm, using a prime factorization, they can find out what is a private key. Then the whole entire premise with which the RSA algorithm was built can be broken when we have a high-end quantum computers. Once they are available, they can run the Shor algorithm in polynomial time. So in a few hours, it will be able to break 1024 bit key. So then the entire RSA algorithm, the key exchange through a public key crypto system will be challenged. So the quantum key distribution essentially shares the symmetric key or a cryptographic key between two locations. And once the key is shared, all the secured communication between the sender and receiver will happen through the normal classical channel, because QKD only solves the key exchange problem. It enables cryptographic key from a sender to be sent successfully to the receiver. Once the key gets exchanged, the green box on the top, the plain text encrypted to a cipher text and decoded by the receiver and again converted back to the plain text, that is normal classical channel. So the QKD essentially solves the bottom of the box, yellow box, where the key from one end is getting transmitted over the quantum channel to the other end, so that the key is shared between the sender and receiver successfully. So currently this, instead of QKD, people are using RSA. So now the RSA getting replaced with the QKD. The traditional encryption decryption, the green box, like AES algorithm, DES algorithm, the symmetrical key algorithms, they remain same. So there is no change there. So what are different use cases for QKD? So if we look at the cases, there are various critical applications. Like, for example, the government communication, like data center to data center communication, and medical information like electronic health records, and between the communication between hospitals, right? And also various defense use cases, right? And then critical informations within the government, all are relevant in the context of QKD. So wherever there is critical communication that needs to happen, whether it is defense, government, or banking, where the quantum key distribution can be used so that the key exchange happens over QKD before the actual communication. So let us now look at various QKD protocols that are in practice. So in terms of the QKD protocols for exchanging the quantum information from the Alice and to the Bob, they can be classified into three categories. One is the discrete variables based quantum system. Another is the continuous variable. The third one is distributed phase reference. So the discrete variable protocols, they work both on a prepare and measure kind of protocol. So they are like BB84, B92, and so forth, and they can be based on entanglement. So there are class of protocols like E91, BBM92, and so forth. So they essentially use phase and polarization of single photons to encode the information so that the receiver can decode and recreate that quantum state. Similarly, in the continuous variable, they use coherent or squeezed states. Whereas in the distributed phase reference system, the arrival of two successive pulses, right, the difference in time or phase or combination. So they form the basis with which the distributed phase reference protocols are developed. So the examples are coherent one-way protocol, a distributed phase shift protocol, and so forth. So essentially, this is the classification of the QKD protocol. So let us go in a little bit of detail of each of the protocol very briefly. So the first protocol that is classical is the BB84 protocol, where the zeros and ones are represented either on a rectilinear basis or a diagonal basis, right? With the horizontal basis, for example, representing a 0 and a vertical basis representing a 1, right? So in a rectilinear basis, a 45-degree angle will represent a 0, whereas the 135 will represent a 1. So depending on, we choose any one of these orthogonal bases and then encode the quantum information, right? Then the receiver decodes and recreates the quantum state. So this is the typical BB84 protocol, even though in hardware, there are not much examples available in this one, but in theory, this is how it works. Many of the hardware systems uses DPR, like COW or DPS. They were predominantly because it is easy to achieve in hardware. But BB84, the theory is like it uses either a rectilinear or a diagonal basis to encode the quantum information using a single photon, and then the receiver can decode and recreate the based on the polarization, right? So they can recreate and try to arrive at whether the 0 is sent or 1 is sent. And if there is an error, so those bits are discarded, and then the ones that are successfully received are again collated, and the cryptographic key is formed. So now let us come back to the one based on the DPR, which is there in that diagram. If you see, the DPR QKD is based on prepare and measure, and within prepare and measure we have COW and DPS. So COW is a very popular protocol. Generally, majority or many hardware supports this coherent one-way protocol, where instead of single photon polarization for encoding the bit, here the coherent pulses are either sent with empty or non-empty pulses. So here you can see from the diagram that if for a bit 0, an empty followed by a non-empty pulses. For a bit 1, it is the other way around, right? A decoy pulse means 2 empty pulses. So this way what happens is, so whenever we want to send a 0, this pattern is used, and bit 1, the other pattern is used. So then if you want to send a decoy pulse, then the other one, right? To check check the coherence of the channel, right? So this way, the encoding will be much simpler as compared to the, let's say, BB84 or E91 and so forth. So in the coherent one-way protocol, the Alice has a random number generator. This bit stream is encoded into coherent pulses, and then the Bob receives it and then decodes it. The presence of a eavesdropper here again will be known through a monitoring line. So whenever the Eve node or any attacker trying to listen to the channel, so he'll be disturbing the coherence of the pulses that are being sent from the Alice. So obviously then the Bob will, the quantum bit error rate will go up. Then the presence of E will be detected by the Bob, and they will abort and then retransmit or use a different channel for key distribution. So this coherent one-way protocol uses this coherent pulses with empty and non-empty sequence to send a 1 and 0 to encode or send the cryptographic key from one end to the other. And in case of differential phase shift, instead of using the decoy pulse and bit 0, 1, here it is a random sequence of phase modulated pulses are being sent, where the phase difference is being measured at the Bob side. So detector essentially records the information based on the arrival of photons, right? So based on the timing information, the Bob will see that whether a 1 is sent or a 0 is sent. So essentially the phase modulated pulses are sent, whether 0 means if the phase difference between two consecutive pulses will determine whether it is 0 or a 1. So then it'll Bob will recreate the random bit stream that are sent from the Alice to the Bob to arrive at the key. So these two are popular protocols that are widely used, both the COW and DPS. So now with that background, let me try to cover what are different practical network deployments that are carried out both in India and elsewhere in the world. So this is one done in China. So what is shown on the right hand side, they have about 2000 kilometer long distance quantum key distribution link. It consists of 4 metropolitan network. In Chennai, we have 1 metro network. A similar 4 network is already available in this particular long distance link of 2000 kilometers. So from Shanghai all the way up to Beijing. So they also have multiple repeaters. For example, all the yellow dots where the repeaters are present, and the red ones are the metro network. And they also have 2 ground satellite links for the satellite QKD link for another 2,600 kilometer away location where they are connected over satellite. So it is really a very long distance network. Effectively, we can consider them to be like 4,600 kilometers they are connected. So both integrated into a fiber optic underground network, as well as the satellite QKD integrated as a single network in China. And each of this metro network, we can see that each of them, for example, Shanghai, where there are multiple point-to-point links, where there are connections going from the same city, multiple access links are there for quantum key distribution. The user institutions, we can call it. So essentially, the green ones are the optical switches, and there are trusted relays, right? Then there are user institutions on the small circle. On the axes are all user institutions. Let me try to. Yeah, this small dots are all user institutions, and the red ones are the backbone connections from where the rest of the things connect, right? Then these are all trusted relays. Whenever we go beyond the 50-kilometer range roughly, so they'll put a trusted relay for the quantum signals to quantum repeaters or trusted relays. The Japanese QKD network was established way back in 2010. So that was mostly to have a secured video conferencing between their governmental broadcasting centers. So they have both point-to-point and point-to-multipoint with the rerouting and path provisioning and the overlay network, right? So that the advantage is like you have multiple paths to reach to the from one point to the other. There is no single point of failure. So there are hierarchical, and even if in the presence of eavesdropper, there is a dynamic switching which enables alternate path provisioned from the client to the server location, or both the parties can communicate over a secured link, ensured that will be ensured all the time. So this is again a really old deployment, 2010 time. So compared to the China and other countries, yeah. And in terms of the European efforts, as we all know, TU Delft is one of the prominent academic institutions. They have established both the QKD network, as well as they have come up with a quantum simulator called NetSquid, which enables simulation of QKD network for performance and physical validation of various protocols and so forth. So this NetSquid simulator is a kind of hybrid simulator which will enable you to work with various QKD settings. So they have really simulated, and also they have a physical network, both connecting different cities in Europe, like Paris to Delft. And then they have both the satellite as well as the fiber-based QKD configurations spread over 377 kilometers in the longer distance. And coming back to our efforts in India, so the Metro Area Quantum Access Network is the MeitY funded project, our Ministry of Electronics and IT funded, which is a joint initiative between IIT Madras, CDAC, and SETS, where ERNET India joined later for especially for SDN-based network management and interoperability related efforts, for especially for real-time fiber monitoring and so forth. And this indigenous hardware is built under the project, is set up at IIT Madras and ERNET India office and the SETS and to NIC. So these are spread over 14 kilometers in Chennai. So from the IIT Madras Electrical Department to IIT Madras Research Park, which is about 5 kilometers, and from ERNET India to SETS about a kilometer, and from SETS to NIC it's about 5 to 6 kilometers. So this Distance is covered both underground fiber as well as sets to NIC is overhead fiber. And they also run multiple protocols like DPS, COW, and PQC, especially for various protocol-related experiment and interoperability-related experiments, and also the hardwares that are used, the QKD nodes deployed and in this setup is completely indigenously developed under the project, led by IIT Madras. It is also India's first QKD network with real field deployment covering this region in connecting to IIT Madras to NIC in Besant Nagar. Yeah. If we look at the network layout topology of the MACAN network, Metro Area Quantum Access Network, so from IIT Madras, it runs the DPS protocol to ERNET. So the Alice node is at IIT Madras and Bob is at ERNET. And sets between ERNET and sets, it runs DPS. And then between another link using another fiber is they run PQC algorithm. And between sets and NIC, we have COW protocol. So this is the kind of topology it is there, and all the nodes are controlled by a centralized SDN controller, where the key management and path provisioning and link monitoring, all of them can be done centrally using a SDN-based controller and a software interface known as DarpanQ, which enables network control and monitoring and key provisioning, key management, all of them, initiating the key exchange, all can be done using a SDN-based software interface. And whenever there is a link, the quantum bit error rate goes above a particular threshold, that means the link is compromised and we should use an alternative link. So, or for example, if the QKD link fails, then I can use the PQC link as a backup path for key exchange. So that is the reason why both the DPS and the PQC were used. So whenever there is a link failure or there is an attack scenario in this particular link, one can use the PQC link. And between sets and since sets is the middle node connecting both ERNET as well as NIC, one can use the path BCE or BDE, right? So this path control and switching is possible from the SDN controller to decide the optical path switching is possible dynamically using a software control. And the entire system supports a centralized SDN-based controller for both key management, key provisioning, and key exchange, network monitoring, and network management. So this is the real physical hardware available at currently operational at various offices in the MACAN project. The Alice node at IITM is here, and the Bob node at ERNET location is at the bottom of the left of the screen. And on the right, we have two Alice nodes at the sets, one connecting to ERNET and one connected to NIC. And the Bob node at NIC. So this way, the point-to-point link from IIT all the way up to NIC can be achieved for key establishment. So as seen from the previous figure, so it is an indigenous firmware hardware. All of it was developed under the project, and various well-known protocols, both COW, DPS, and PQC were all tested in this real field environment, and also the multi-vendor interoperability, having additional hardware from CDOT was also added to the system for interoperability related experiments. That I will try to cover a little later. So one of the key requirement of the QKD system is the reliable fiber link. So the communication link has to be really of good quality, because the single photon transmission is challenging if we don't have a quality fiber available for transmission. Because if there are, let's say, if the splice or the connectors are not clean, or if the fiber is of poor quality, for the classical communication, it may not have that much of an impact, because the higher layer protocols will take care of the retransmission and all the error handling. Whereas in the quantum scenarios, the error will be seen as a link failure or an Eve node presence. So those scenarios are to be, if they need to be addressed, then we need to have a good quality fiber available between this. And the link monitoring is quite essential, both for any fiber cut or fiber having any issue in the link, or even if the Eve node is present in the link, those scenarios needs to be taken care. So they require real-time fiber monitoring using what is known as a OTDR, optical time domain reflectometer. Hello. So OTDR measurement of for all the links is crucial in this particular project. So the real-time fiber monitoring is done through OTDR measurement. So the OTDR measurement will tell us what is the link loss of the individual links in the metro area quantum access network. So yeah. So the other project that we have executed in at IIT Madras is on the AOC testbed, Advanced Optical Communication Testbed, which is an IIT Madras-led initiative where the ERNET India work package is on the QKD network security. Essentially, the idea is to emulate an attack scenario in the QKD link. For example, the topology that I have shown earlier, if an Eve node is present at a particular link, that means that this link is prone to attack or some attacker is present. So can I use link 2 instead of link 1? Can I dynamically switch from the Alice Bob communication using link 1? Can I dynamically switch and change it to link 2 whenever there is a presence of an Eve node that I detect? How do I detect? So that particular link detection or the failure scenario will be detected using what is known as a Kuber monitoring, like quantum bit error rate. Whenever the link quality is poor or an attacker is present in the link, it will be reflected in the Alice and Bob measuring a higher Kuber rate. The quantum bit error rate will be higher. So that means that somebody is either present or the fiber is completely cut. So in both the scenarios, the quantum bit error rate will go high, but the quantum bit error rate will go high. And also the link cut can be monitored using a different, this OTDR measurement will show a link cut differently. So we will get to know whether it is really a link cut or a Eve node being present. So in those scenarios, we are supposed to use a different link for our key exchange. So in this project, we have intended to emulate various attack scenarios like a denial of service attack, fiber tampering attack, and photon number splitting attack. So multiple attacks have been emulated in a real field network to measure the quantum bit error rate dynamically in the network, so that we can provision the alternate path for the Alice and Bob to use using SDN-based path provisioning controller. So that is part of this particular objective of the project. So the hardware setup for this particular experiment is an Alice node, a sender, and a Bob node, a receiver, and a Eve node, which is a eavesdropper. Eavesdropper will emulate various attack scenarios. The Eve node can be connected either at the Alice end or a Bob end or anywhere in the fiber link. So whenever the Eve node has multiple options to emulate the attacks, fiber tampering, denial of service attacks, and all. So once these attacks are injected or the noise is injected into the channel, so the Alice and Bob quantum bit error rate will go high, and then they will either need to switch the path or abandon the communication for this. So this field trials were done both in the Makan test bed as well as in the defense army site in the Dakshin Bharat area in Chennai. So we have connected about 3-kilometer link between the Dakshin Bharat head office and the a training institute, their training institute, which is 3 kilometers away in Chennai. So the Alice is placed in the head office, and the training institute has a Bob, which we carried out the experiment for various attack scenarios. So, and further to this, we have also done along with the encryptor and decryptor. So one is the key exchange part of it. Another is after the key exchange, we need to actually do the real transmission. The key exchange happens in the Alice and Bob node, because the Alice and Bob exchange the key using a quantum communication link. Once the key is transferred, the key is transferred to the PC. The PC is nothing but it is going to run an application, encryptor, decryptor. So the encryptor, decryptor are two different devices. We can run it on a standalone PC like a laptop or a PC, or it can also be run in a specialized hardware. For example, the CDOT has an encryptor, decryptor solution as well, so that our solution is ready to use. For example, we connect an encryptor, decryptor in the network, then any data that we send, we can route it through the encryptor, and then complete channel is encrypted, and then there is a decryptor at the other end, which will decrypt the data, and then we get it. So the entire link, the classical communication link in the pink color, used for, the green one is used for key exchange, the pink one is for synchronization, and the green one is the top green one is the actual encryptor, decryptor between here and this box and this box. This is our encryptor, decryptor, and these are Alice and Bob. And this is the Eve node. Red color one is the Eve node. So the encryptors are small boxes, encryptor, decryptor. They are nothing but running an application, like a symmetric application, like a DES, AES algorithm. So that is why it can be done by a simple laptop also. So the main part is the key exchange between Alice and Bob. Once the key is exchanged, from the key management system, the key can be transferred to the PC or a laptop for people to run the symmetric algorithms like DES or AES, so that the encrypted data can be sent to the other side, so that the decryptor can decrypt it. So this is the physical test that we have done it in the army site. Yeah. So whenever there is we can see from this live streaming application, where with the eavesdropper and the Alice Bob key exchange plus the video streaming application, all that is integrated, where whenever there is a eavesdropper present, so the quantum bit error rate, we can see that the Q-bar value goes like 40%, which is well above the expected value. Anything above 20% or 10%, so we need to suspect that there is somebody eavesdropping into the channel, or there are more error rate. Anything above 20% means essentially either the link is compromised or it is better to abort the communication. So whenever we have the Eve node emulating the attack scenarios like a fiber tampering attack or a denial of service attack, then the message will pop up saying that the link is compromised. You can see at the red color tab saying that the quantum key distribution system Alice security compromised. So this means that whenever the quantum bit error rate goes above the 40%, this communication live streaming will get stopped, or if it is a simple data transfer, it will be aborted. So these were the scenarios where EVE node, whenever it is present, so the quantum channel will bring a lot of or will result in a lot of error. Quantum channel will introduce a lot of error. Kuber rate will go up. Both Alice, the sender, and the Bob, the receiver, both will experience the quantum bit error rate, and the EVE node presence can be detected. So this is what when we meant that the key, when it gets exchanged from the sender to the receiver, we can 100% be guaranteed that the key is received by the receiver untampered. So without anybody listening into the channel, the key gets exchanged. That means that the key is securely exchanged to the Bob side. So another test that we did at IIT Madras is using their campus network with the multi-core fiber testbed that is available in the IIT Madras campus under the Advanced Optical Communication testbed. So they have 8-kilometer underground fiber. They are special fibers which are multi-core fiber, where in single fiber there are 4 cores. So essentially, we can do 4x communication in a single strand of fiber. So when we use this 4-core fiber, what are the challenges when we send both quantum and classical channel? What are the interference and crosstalk? When we send both quantum and classical in the same fiber, what are the challenges? These were studied in this particular experiment. Under the Advanced Optical Communication testbed, the industry partner which has that has manufactured the multi-core and single-core fiber was laid in the underground of the IIT Madras campus in with a round trip of 8 kilometers. Beyond 8 kilometers, you can loop back and try to have multiples of 8 kilometers for our testing. So this multi-core fiber, both aerial as well as underground, is available for the experimental work. So especially here, the study was more to understand what are the interference-related challenges when we have both quantum and classical going in a multi-core fiber. That was studied and validated in the testbed environment at IIT. Yeah. So similarly, this plot will give an idea in terms of whenever there is a attacker present, we can see that the Kuber goes from normally the Kuber is well below the 10%, right? And whenever there is a E present, the Kuber value goes to 38%, right? And when the fiber tampering happens, it is going to 16%. When it is both Trojan horse and fiber tampering at the same time, it goes to even 50%. So this is the Kuber value versus the attack scenarios. Injecting multiple attacks using a EVE node, what is the result? Similarly, the Kuber, higher Kuber means that the lower key rate. The key rate will come down. So whenever the Kuber values are lower, that means you are having a good key rate. Your keys are exchanged without any errors. So that means keys are received from the Alice to the Bob without having any loss of qubits. So you can see that whenever the Kuber value is high, the key value drops. Similarly, the Kuber value is high, the key value gets dropped. So they show that the peak key rate is about 1.2 kilobits per second. So if it falls below a particular threshold, that means that there is a EVE node present in the link. So then it is a security is compromised, and that means either the key should not be used, or we need to retransmit using a different fiber link for a secured key transfer. And we have also studied the coexistence issue in a different project, MIT funded project jointly with NSUT Delhi and IIT Indore, where the study was to see can we send both classical and quantum on the same fiber, or in the existing fiber network without using dedicated fiber? So what are the kind of challenges and what is the advantage, disadvantage is getting studied in this project. So, and this is being carried out is an ongoing project. And the other activity that CDOT has done, similar to the Macan project, CDOT has done field deployment of their QKD hardware between the CDOT Alice node is deployed at the Sanchar Bhavan, which is a DOT office at one side, and the NIC at CGO complex in Delhi. So they are about 10 to 15 kilometers apart. So from there to NIC office, they have successfully demonstrated the key exchange that it is currently operational. So these are devices that are currently available for their experiment and testing. So this is a practical deployment in a fiber link between DOT office and NIC office in Delhi. And another activity by an academic organization is the Raman Research Institute. They have carried out free space optical QKD link about 50 meters apart between two buildings. Yeah. So this is the this is my last slide, and thank you for the opportunity. And if there are any quick questions, I can take. Yeah.
Thank you, sir. We'll now take a few questions from the audience. Thank you. It's now my pleasure to introduce our next distinguished speaker, Dr.
Sir,
Sashank
thank you
Gupta.
so much. Wait, hello, please wait.
Yeah.
Thank you
Yes,
so
ma'am.
much for your talk, sir, for the time, and for your very interesting lecture on the practical applications of quantum and its application of cryptography to the and to the quantum community. It was really interesting to see the practical implementation that you have done with the assets and IIT Madras. From the behalf of the management and the faculty team of our program, we extend a heartfelt thanks, and on behalf of the participant side. And a few of them have asked for the slides. If sir permits, I will share the slides. It is based on the if any confidential information is there, then we will not be able to share the slides. Otherwise, it's fine. And thank you so much, sir, for your time and for accepting our invitation and for your continuous support towards the faculty of KCG College of Technology and to the students. Thank you, sir.
Thank you very much. It's a pleasure talking to all of you. Yeah, thank you.
Participants, you can take a short break and we can again join back after 10 minutes. Our session will start again at 7:45, and the session will be by Dr. Sashank Gupta, and we will look forward to his session. Okay, thank you. You can remain online and once the resource person join, we will intimate you. Thank you.
Dear participants, attendance link is shared on the chat. You can post your attendance for the first session.
யாருக்கு ரசம் Hello.
So can you share the slides?
Yeah,
We'll
yeah,
just check if it is. Yeah.
sure. Right. Can you see the screen?
Yes, sir. Yes, sir.
Okay, wonderful.
So we will have a brief introduction and then we can start, sir.
Right.
Yes, sir.
It is now my pleasure to introduce our next distinguished speaker, Dr. Shashank Gupta, research lead in QNU Labs. Dr. Gupta holds an integrated PhD in quantum information theory and SN Bose National Center of Basic Sciences, where he focused on the foundations of multiplier quantum resources. He then applied his expertise to commercial world, working in QNU Labs, an Indian startup at the forefront of quantum cryptography. During his tenure, he played a pivotal role in a team that successfully broke distance barriers in quantum key distribution, achieving an impressive 150-kilometer point-to-point connection. After serving a postdoctoral research at OIST in Japan, he has since rejoined QNU Labs to continue his work towards a quantum safe Indian subcontinent. His research interests are wide ranging and include quantum cryptography, post quantum cryptography, and quantum communication networks. Please join me in extending a warm welcome to Dr. Shashank Gupta. Without further ado, I hand the floor over to Dr. Gupta.
Yeah, thank you so much. So, yeah, I'll reshare the screen and then we can have a discussion on this topic, right? Okay, just a minute. Yeah. Right. So, I hope you can see my screen, right? So, topic is so I was told by Professor Deepa to cover quantum key distribution in a manner that is easy to follow. Try to demystify why such a technology is essential and how we can uh, follow the journey of single photons to realize such a technology and can have secure communication, right? So uh, I understand that FDP is on say quantum computing, right? So I will try to justify my talk somewhat at the end how such a distributed quantum key distribution network can serve as a uh, distributed computing tool, right? How we can utilize, say, quantum key distribution network to perform, say, distributed multi-party computation, right? So that will kind of justify the main theme of this FTP. Uh, and Quantum communication will try to cover nitty-gritties of the quantum communication, right? Okay, so now let me just yeah, share this part of the presentation, right? To cover the basic outline and then take it forward, right? So I will first try to introduce the notion of ideal security, right? Why ideal security is kind of essential in a world which is digital and well connected, right? And then try to match this ideal security requirement, right? How quantum uh, can offer very critically through its fundamental principle, how it can serve the requirement of ideal security notion, right? Then we'll talk about, say, quantum communication modes apart from quantum key distribution. What other possible ways of doing, say, quantum communication, right? As a theme, we'll try to cover somewhat on secret sharing, quantum secure direct communication, dense coding, all that, right? In a brief one slide, right? Then like essentially main part of the presentation will start where we discuss the stages of point-to-point quantum key distribution, what it takes to realize quantum key distribution using say photons, photonic degree of freedom, right? And then we'll try to see how a point to multi-point QKD looks like, right? Why we named it as chakra, we'll justify that. And then we'll briefly touch upon other communication mode, which is quantum secure direct communication, where we do communication without generating keys at first place, right? Okay, so to begin with, uh, uh, like I have to justify why such a transition to quantum is required. So then I have to touch upon fundamental of current cryptography, right? And when we talk about current cryptography, uh, most of it is based on public key cryptography, right? And very fundamental to public cryptography is hard problems, right? But the question that I am asking is whether hard problem exists. Is there a proof, right? Whether at very fundamental level, nature offers the existence of hard problem, right? Why such questions are relevant? Such questions are relevant because of this gentleman, right? Our RSA algorithm is based on a hard problem called determining the factorization of large number, right? So classically speaking, when we take in account for only classical resources, then it is a hard problem, right? Because we don't know any suitable algorithm which can say reduce its complexity to polynomial like a scale, right? But this gentleman using quantum resources gave an algorithm called Shor's algorithm, right, in the year 1994, and diluted the complexity of factorization to polynomial. And think if things are say uh, polynomial in complexity class, if it belongs to polynomial scaling, then it is no longer hard, right? So one example we saw, right, factorization, which seems to be a hard problem, classically is no longer a hard problem, right? And if it is no longer a hard problem, then we have to change the foundational blocks of cryptography, right? We have to replace the current crypto stack, right? We have to figure out different ways of doing cryptography, right? Uh, so that is like precisely I was talking about, right? So classically, if I keep on increasing the number of digits of a large number, right, then number of operations which are required to factorize the number keep on like increasing exponentially, right? Using the best known classical algorithm called field sheaf. But using quantum algorithm, you can see that it is no longer exponential. It is like polynomial d cube along with some constant factor, right? So then increasing the size of number will no longer be helpful, uh, provided a fault tolerant quantum computer is there, right? Here I took help of some of the references and quoted some of the resource requirement for breaking down, say, RSA 4096 Diffie-Hellman 521 qubit. What is the requirement? How many logical qubits will be required? And then say the amount of time which is required to factorize such a number, right? And complexity uh, is kind of mentioned. So that is what I was talking about. So since RSA is no longer secure because we know the algorithm, right? Only missing part is a large scale quantum computer. But we all know that quantum computing is one paradigm. There is advancement which is happening in AI vertical, also on HPC vertical, and combined together there are sophisticated algorithm which can keep on decreasing this gap, right? So maybe we might be sitting somewhere over here, right? Using current hardware resources, right? And this gap is diminishing very fast with improvement in the technology, right? So we have to think for migration to better alternatives, right? But before discussing on those better alternatives, let's take a step back and think about what are ideal security demands, right? At very fundamental level. Forget about cryptography. What basically we want in order to achieve ideal security, right? So motivation wise, we are pretty clear. Things are digital. We want faster, better, and secure ways of doing communication, right? We have to take care of the backdoors which are present. We have to address the vulnerability of the physical link. So motivation wise, it is pretty clear. So let's discuss on the ideal security scenarios, right? So there is no security with respect to hiding the algorithm, right? So algorithms are in public domain, right? Only security which is there in any crypto system is based on the how good is the key, right? And we judge when we judge goodness of a key, we think of factors like whether it is truly random or not, right? Whether if someone tries to copy the key, can I can the trusted party get notified, right? If someone is manipulating the key or trying to tamper the key during its say generation, distribution or management cycle, whether I can or the trusted party can detect it, right? So combined together, these four requirements serve as ideal security requirement, right? And we'll see how fundamental quantum principle try to achieve these ideal security requirement, right? So now we discuss the ideal security requirement. We discuss the vulnerability of current crypto structure. What are the alternatives? So there are two alternatives to provide post quantum security, right? One approach is called quantum resistant or quantum safe cryptography. Another is unconditional secure based on, say, quantum mechanical principle, which provide information theoretic security, right? So this is fundamentally different way of achieving, say, achieving key distribution, right? Using fundamental quantum principles and fundamental quantum particles. So this approach is was not there previously. This approach is again based on mathematical algorithm based on public key cryptography. We are finding different ways of doing public key cryptography on the problem which are, say, uh, conjecturally proven that they are secure even if a quantum computer is there at adversary hand, right? So here we are again finding some hard problem which are hard even if quantum computer will be there, right? So this paradigm belongs to post quantum cryptography. And IST being an organization in United States who take care of, say, security standards for crypto system, have given recommendation for both key encapsulation mechanism and digital signatures based on mainly, say, lattice based cryptography, but there are other alternative based on code based and multivariate polynomial, right? And my talk will be mainly on the right side of the things, right? Where we are trying to achieve, say, trying to solve key distribution and randomness problem, right? Using fundamental quantum particles. And we'll discuss about, say, quantum key distribution, quantum secure direct communication, and quantum secret sharing, right? So whatever we discussed here, right, using the right side of the next slide, one can understand that, okay, quantum principle offers intrinsic generation of randomness. So whatever keys will be generating using quantum particle will be truly random. So this notion is satisfied and high quality. If keys are random, then like security is top notch for any algorithm. The other two requirement can be served using, say, the no cloning principle in quantum mechanics, right? You cannot copy any arbitrary non-orthogonal state that is forbidden over there. So whatever key, classical key material that is coming from, say, underlying quantum state, if underlying quantum state cannot be copied, every time the classical key you will be generating out of those state will be a different key material, right? So this notion is also satisfied. Now we know that quantum state, when tapped, right, you cannot do read out of a out of a quantum state without disturbing them, right? So information readout without disturbance is also forbidden for a quantum state, right? As soon as you try to get some information out of quantum system, you disturb it, right? Or one can put it this way: the act of measurement destroyed the superposition quantum state, right? And act of measurement forces a quantum state wave function to collapse to one of its eigenvectors, right? So all that combined together offers a primitive where you can detect any sort of tampering event happening on a quantum system, right? Okay, so I almost touched upon it, right? So we'll move faster on this part, right? So it fundamental unit of information for classical system is bit, which can be in a state 0 or 1, whereas fundamental unit of information for quantum system is qubit, which can act in arbitrary superposition of 0 and 1, where arbitrary superposition is denoted over here. Alpha and beta could be complex number, and when we are representing it in a block sphere, the parameterized description of alpha and beta is over here, right? I require two parameter theta and phi to describe any arbitrary qubit in a block sphere, and the range of theta and phi is denoted here, right? Theta is the angle with respect to y-axis, and phi is when I kind of uh, uh, take a projection on xy plane, what that projected vector has an angle with respect to x-axis. That two variable describe any arbitrary qubit. Right? Now, act of measurement will collapse this particular uh, state into either 0 or 1 with probability mod alpha square over, say, 0 state, and with probability mod beta square over 1 state. Provide these are normalized, so mod alpha square plus mod beta square is equals to 1. Okay, so what ideal security requirement quantum superposition can provide? Just a recap. It can provide, because quantum like superposition vanishes during the act of measurement, right? And it is fundamental reason behind, say, interference effect that you observe in a quantum system, right? So this particular act of, say, tampering can be detected during collapse of, say, superposed state, right? And also this collapse is truly intrinsic random, so random notion is also satisfied over here, right? This you can see over here. It's a very beautiful experiment in quantum mechanics, where you take double slit, you you probe these double like slits using a stream of quantum particle which is coming one at a time, right? Now if someone is trying to see whether the particle is passing through slit S1 or S2, this act of just observing whether the particle is passing through S1 or S2 kind of disturb the particle, because how you observe those particle, whether it is passing through S1 or S2, you will project some electromagnetic wave, right? In order to observe that, and those electromagnetic wave will kind of interfere with the incoming particle, and whatever the interfere pattern P12 you were supposed to observe will no longer be available, right? So this disturbance due to measurement is responsible for detecting, say, tampering event when you are creating a technology out of, say, quantum mechanical or quantum particles, right? Then no cloning theorem I briefly talked about. Here is a proof that if you take some unknown quantum state alpha, which is a superposition of 0 and 1, then when you try to clone it, you will be in a state of ambiguity. So proof is pretty straightforward. Just you have to understand what does cloning mean. So when you take a sheet of paper you want to clone over a photocopy machine, right? You have that original copy, you have a blank copy, and you apply a cloning operation, you end up with two copies of the sheet a original sheet and a photocopied sheet, which are say similar, right? So cloning operation means when you try to mix it with a blank state, you end up with two copy of the state, right? If you apply same thing on orthogonal state, there's no problem. You took say zero state, take a blank state, you end up with two zero state. You took a one state, a blank state, you end up with two one state, right? Post cloning operation. For a general state, if you apply this logic, right, on say alpha state, which is a0 plus b1, then you will end up with a times 0 0 plus b times 1 1 following these two equations. And you, if you take the fundamental idea of cloning, you will end up with two copies of alpha state. And if you apply say uh, uh, a kind of product of these two state, you will end up with equation 2, right? And now equation 2 and 1 are not same until AB is equals to 0, right? If AB is not equals to 0, A times B is not equals to 0, then 1 and 2 are different. And if they are different, then cloning is not giving you.
Sir, excuse me, sir.
Right. Yeah, go ahead, please.
Sir, is the slide visible from your end?
I have shared it, but I think there's some problem, so I will reshare it. For
Okay,
how
okay.
long it was not visible?
Just 2 minutes.
I hope you can see it right now.
Yeah, right now we can see.
Okay.
Thank you,
Thank
sir.
you for letting me know. Still, it is visible, right?
Yes, yes.
Okay. So I was talking about this no cloning theorem, right? So you will end up with like equation 1 and 2 being different, coming out of a same combination of state and cloning operation. If they are different, then quantum mechanics forbid cloning operation, right? So if cloning is not possible of quantum state, the classical key material that you are getting out of those quantum state will always be different, right? Uh, so essentially this requirement is also satisfied by no cloning theorem, which is yeah, which is this, that the key should not be copied, right? So every time you will end up with a different key. Now let's talk about some of the quantum correlation, right? So superposition is very fundamental to quantum particle, but if you take say two quantum particle and not just one, then you can observe other set of quantum correlation, right? So for example, quantum entanglement exists when you have two particles uh, in such a manner that the joint state cannot be described by uh, a convex combination of local state. We'll discuss about this quantum entanglement, right? Then quantum steering is even stronger correlation. Well, non-locality is even stronger correlation than steering and entanglement. And this, like in this paper, the authors describe the hierarchy of quantum correlation, right? So you can see that Bell non-local state will be steerable. It is also has entanglement, right? But it is not other way around. There could be quantum entangled state, which may not be steerable and Bell non-local. Similarly, like there could be state which has say quantum discord, non-zero, but they may not be entangled. They may not be steerable. And quantum coherence is the weak most quantum correlation over there, right? So let's now understand quantum entanglement, how to generate it in say photonic degree of freedom, right? So mathematically speaking, if the joint state of the two quantum system AB cannot be represented as a combination of local description of say subsystem A and local description of subsystem B. Here this represents the tensor product between say subsystem A and subsystem B, right? If such mathematical description does not uh, holds true for a system AB, then quantum entanglement is present in that subsystem. How to understand and what are the implication of quantum entanglement? That can be pretty well understood using these Bell state, right? These four states are maximally entangled uh, uh, maximally entangled system for two quantum particles, right? Now let's try to understand what are the implications. So assume you are starting with such a state, which is say 0 0 plus 1 1 by root 2. this system say belong to particle A. If you perform the measurement on the particle A, you will end up with either state 0 0 or 1 1 with probability half, right? Because that is the combination. Now I assume that you end up with say 0 0 state, right? And now particle B is performing some measurement, then with 100% probability the particle B will also get outcome as 0. If particle A got the outcome as 1, then the post measured state will be 1 1. And now if particle B performs some measurement, right, it will always with 100% probability end up with outcome 1. Similarly, the other states follows, right? So that is the implication of entanglement, right? But you cannot do faster than light communication using entanglement, because if you take say partial trace out of any system, you will end up with maximally mixed state at other system, right? So you have to do some uh, classical exchange of message in order to do say some communication using entanglement, right? Now how to generate a say entangled particle in a lab setup, right? So for that, this particular picture, uh, it shows a spontaneous parametric down conversion process where you are injecting a high intensity pump laser beam on a nonlinear crystal, and then you will end up with for provided conservation of energy and momentum will be there. You will end up with two photon which will have half the intensity of the uh, incoming photon, right? These photon are called signal and idler photon, and whatever say photon will be there at the intersection of these two cone, you will not be like idea about whether they are say vertically polarized or horizontally polarized. So these two photon which will be at the intersection will be entangled photon, right? Okay, so how to witness entanglement? So this gentleman, John Bell, gave a very beautiful equation and experiment to witness entanglement and witness Bell non-locality. So what is the experiment? You can understand it. Suppose you are given two black boxes, right? One at say your institute, right, which is in Chennai, and say at my place which is in Bangalore, right? Now what these boxes contain? These boxes contains some object which are either round in nature or star shaped, and they have either green color or red color, right? Now classically they will have definite shape and definite color. So if you determine what is the probability of getting a particle which is round in nature and green in color, and say a object which is star shaped and green in color, these combination of probability, you keep noting them, these joint probability at your station and me noting at my station, then we have to calculate say some combination of these joint probability which is there in Bell inequality. Then classically the max value which I can get for such a inequality is value 2, right? But quantum mechanically, if these two boxes are entangled, whatever quantum particle they contain are entangled, uh, then a particle could be round shaped and red in color also, star shaped and green in color also, and both ways with some probabilities, right? And act of measurement at this object will have some influence on act of measurement on these the particle on these boxes, right? And when you keep on performing say calculating these joint probability, you will end up with violating this Bell inequality, and then you can understand that okay, no classical resources can violate such inequality, but yeah, entangled particle with a value greater some threshold of entanglement can violate such inequality. So it's a uh, a beautiful just you are calculating some correlation out of a subsystem, and you can witness say entanglement, right? So that is beautiful. Now let's jump on the quantum communication mode, uh, and yeah, so either you can achieve these communication mode using say entanglement and other quantum correlation, or you can also achieve it using say single photon uh, algorithm as well, right? So what is the intention? I want to solve some cryptographic problem, right? So in order to do symmetric key cryptography, I require same key at two station, right? Which could be say hundreds of kilometer apart or even thousand of kilometer apart if they are connected by satellite, right? So I want to solve a problem of key distribution, right? So quantum key distribution typically does that. What are its stages? We'll discuss more in detail in upcoming slides, right? In quantum secure direct communication, the objective remains same. I want to do say secure communication, but without doing say key distribution at first place, right? So how to do it? There is a drawback that roughly distance reduces by half. So these communication mode have not gained much attention, right? People focus mainly on the quantum key distribution. In quantum secret sharing, the idea follows from Samir secret sharing, right? Where few parties, you have to have a number of parties above a threshold, which have to collaborate in order to figure out a secret. And now secret could be a classical secret or it could be a quantum secret, right? So both alternative are there. In quantum teleportation, I want to teleport a quantum state from a lab at say Bangalore to a lab at say Chennai, right? Without physically transmitting the quantum particle or the quantum state, right? So these two stations, suppose, are connected by entangled state, then I will perform some local measurement at my lab in Bangalore, and I will be teleporting uh, the intended unknown say qubit state from my lab to your lab without physically sending anything, right? Just an exchange of classical messages over internet will suffice. But yeah, we need to have some entangled state to be inherently present in order to do quantum teleportation. In superdense coding, again, these labs are connected through entanglement. Here, the objective remains that I want to send, say, exchange a 2-bit of classical message uh, by say communicating 1 qubit state, right? So because using only 1 qubit, 1 unit of say quantum state, I'm doing 2 unit of classical message exchange. That's why it is called superdense coding, right? Okay, now rest of the talk will discuss and demystify quantum key distribution uh, point to point, uh, and then we will discuss how to do say point to multi-point QKD also. So in quantum key distribution, the objective remains that I want to come up with symmetric keys at two stations, Alice and Bob, which are separated by say hundreds of kilometers through either optical fiber, they are connected by optical fiber, or it could be a free space satellite link. And in that case, distance could be even longer, right? But objective remains same, that I want to derive some symmetric key, right? Which is classical in nature. Key means a random string of 0 and 1, right? So that is the objective. And usually for doing symmetric encryption using AES, the key size requirement is 256 bit, right? That keep on shuffling because these substation will continuously be generating symmetric keys, right? So one has a freedom to say change the key as and when required, right? So how to achieve that objective? So first, Alice and Bob node will be authenticated and synchronized, right? And usually authentication is done using pre-shared keys to begin with, and as first round of QKD happens, then that pre-shared key is shuffled by some part of the key generated out of a QKD process. Synchronization up to accuracy of 10 picosecond is required, and that is achieved by another optical signal, which is say classical in nature, for achieving say synchronization. Or if you have atomic clock between two nodes, then that optical link is not required, and you can have synchronization maintained using atomic clock, right? Once authentication and synchronization is achieved, then quantum stage begin, where you can do this stage either using say quantum entangled pair or say using single photon approach, right? So initially Alice station, if it is a single photon like prepare and measure kind of scheme, then Alice perform a quantum state preparation step. It prepared the quantum state and send these state uh, out through say optical fiber at the Bob station where Bob measure it. If it is connected by entanglement, then preparation doesn't happen. Both Alice and Bob perform the measurement, and because their outcome are correlated, they can generate the raw key, right? Once whether you do it using prepare and measure scheme or entanglement based scheme, at the end of measurement, your quantum stage terminate, and rest of the stages are classical in nature, right? So once the measurement is performed, uh, these two nodes end up with some uh, raw key, right? Some random number at both the ends, which might be containing some error and some problems, right? But yeah, so a set of post-processing stage begins. First stage is shifting, where Alice discard all the data for which Bob does not get a detection, right? Because channel is noisy and lossy in nature, most of the particle which Alice is sending will be will be lost during the transmission stage, right? So in shifting, Alice discard all what Bob has not received, right? In parameter estimation, they determine what is the rough quantum bit error rate of the channel, what is the transmittance of the channel, right? For which they exchange some of the raw key, right? That raw key will then no longer be used for coming up with final pair of keys, right? Then began with a stage called classical error correction, uh, where Alice and Bob eliminate whatever error was caused by quantum channel, provided the rough error is below the threshold defined for a QKD protocol. It is say 4.12% for a DPS protocol and 11% for BB84 protocol, right? So rough tuber should be below that value. Then comes a very important stage called privacy amplification, where Alice and Bob compress their raw key, uh, and this compression percentage is determined by whatever information leakage is happening in say error correction stage, and what is the adversary model that you are taking for say your QKD security, right? Usually for individuals attack based model, the Cuber upper bound is more, but for collective and coherent attack, it will be very strict, right? Once you compress the key, you determine the hash value of those key for say key verification, and then your post-processing states, you are done with the post-processing stage. The final stage is key management and fetching stage, where you will be assigning the key ID for every 1024 byte of string that you have generated up to this stage, right? And you will be securing it in a secure vault, right? Your application connected to your QKD boxes can fetch those keys using a standard protocol. It could be skip or it could be HC GS014 interface is what we support, but different QKD boxes support different fetching interface. But these are the standard interface that they should support. Yeah, so our boxes supports both connection of Cisco routers and say any other router which supports HCGS014 interface. Now, every stage that I talked about will not be ideal in nature. There will always be some failure probability associated with either the quantum stage or classical stage. So these numbers denote failure probability with respect to a stage, and combined together, what is the overall failure probability of say our most QKD, right? So it is 3 into 10 raised power minus 12, which means in every say terabyte of key, like terabyte of key that we generate, there could be uh, one key which might be unsecure or it might be uh, uncorrect, right? So that is what the failure probability denotes. Now let's try to understand the very fundamental and famous protocol BB84. BB stands for Bennett and Brassard, who gave this protocol in the year 1984 in our Indian city, Bangalore. They came for a conference, and that's where they presented this protocol, right? Okay. So now to understand this protocol, uh, let me just check whether my slides are still visible. Okay, wonderful. Okay, so in order to understand BB84 protocol, you first have to understand, say, photon polarization, right? And for that purpose, let's understand these four states, right? Now, we have to understand two bases in order to understand BB84 protocol, because two bases are required for this protocol, right? So rectilinear basis means the two state in that basis could be either horizontal or vertical, right? I assign 0 for horizontal state, 1 for vertical state, and combined together these two states form rectilinear polarization basis. For diagonal polarization, I have diagonal and anti-diagonal. For diagonal state, I assigned 0, and for anti-diagonal, I assigned 1, right? Combined together, these four state I'll be using for doing BB84. How to understand these representation? So you can understand it with respect to, say, degree of polarization. 0 means horizontal, 45 means diagonal, 90-degree means vertical, 135 means anti-diagonal, right? And that is what the color follows, right? Now, what happens at Alice node, right? So Alice is randomly creating these four states. So for that, it randomly picks a basis state, and then with 50-50% probability out of those like basis state, it generates one out of them, right? So first a basis choice and then a state. So suppose Alice is generating these basis state randomly, and it will be sending it via a communication channel. At Bob station, it will be receiving those state, and it will be choosing its basis choice independently, and will be performing same measurement of these incoming state in either rectilinear or diagonal basis. Whenever their basis choice matches, their outcome is correlated, right? That is pretty straightforward through this table. So suppose Alice bit sequence is 110 100 110 100, right? Now Alice basis choice is denoted over here, right? So Alice chooses a diagonal basis for this one, and because bit sequence is 1, it will generate a anti-diagonal state clear from here, right? Here Alice chooses a basis called rectilinear polarization basis. Bit sequence is 1, that's why it generated vertical. Again, rectilinear basis choice, but bit sequence is 0, that's why it generated horizontal, and rest of the thing follows. Bob independently chooses diagonal or rectilinear basis. So here it chooses diagonal basis. And also Alice has generated diagonal, like state in a diagonal basis. The outcome is correlated. So when Bob perform measurement, Bob will get outcome as 1 because shared sent state is anti-diagonal, right? So this is Bob measurement. Here also basis choice matches, and that's why their like prepared state, like bit sequence and outcome also are correlated. Here basis choice mismatches, and then outcome may or may not be correlated. Most of the time it will be incorrect, right? So here things are not matching. Here again basis choices matches, outcome are correlated. Here basis choice mismatch, outcome are not correlated, and rest of the thing follows. Post Bob measurement, Bob will communicate its basis choice in a public channel, and Alice will discard all the data where Bob basis choice is not matching with Alice basis choice, and wherever it is matching, that will form the key. This is the symmetric key which will be there at Alice station at as well as Bob station, and they can use this key for doing, say, uh, encrypted video communication or encrypted exchange of text message. That encryption you can do either using some symmetric key cryptographic algorithm, or you can do one-time pad. For one-time pad, your key size should be same as your message size, right? Okay. Any question at this point? And then I will move with whatever we are doing at QNO Labs. So 30 seconds if you have anything to ask at this moment. Okay, I'll just have a look at the chat box in case there are any question over there.
Thank you, sir. Thank you for your fascinating talk. We'll now open the floor for questions.
No, I have some slides remaining. I just took a pause for a moment, right? Okay, there are no question. This all is symmetric key. Any concern regarding asymmetric key? Right, so asymmetric key, I told, right, post-quantum cryptography is a approach to solve the concern of asymmetric key. At the end, even for asymmetric key cryptography, right, we try to do say exchange of public-private key pair, and then we perform key encapsulation mechanism, right, where we come up with symmetric key post say key encapsulation mechanism, because uh, symmetric key cryptography is more secure and more efficient, right? So even public key cryptography follows symmetric key cryptography. So if you can solve the key distribution problem, then both things are kind of same, right? But if you want to do say don't want to do exchange of quantum particle and all, and follow say public key cryptography stack, then you have to do post quantum cryptography way of doing things, right? You have to migrate your crypto stack with post quantum cryptographic variant. Okay, now I will again uh, come back and discuss what protocol we use, what is our point-to-point QKD look like, right? So we follow differential phase shift protocol because in optical fiber, differential phase is more robust than polarization, right? So we follow differential phase to encode information, and the protocol that we use for doing QKD is differential phase shift. We add decoy on top of it with the intention to increase the distance, right, and to provide security against photon number splitting attack. Okay, so spoke is basically your Alice station. Hub stands for Bob, and this terminology is coming from point to multi-point QKD, right? So this is how our 19-inch 2U QKD boxes look like, right? Yeah. So at Alice station, first quantum state preparation happens, right? So for that, like single photon generation rate commercially is very limited. So we mimic the behavior of single photon using V coherent pulses, right? V coherent pulses are optical pulses where intensity corresponds to single photon regime. We reduce its power such that every optical pulse contain a fraction of photons, right? So photon wave function is kind of distributed over many optical pulses. So we take a laser source which is having a wavelength of 1547.12, so corresponding to 1550 nanometer. This is CW mode laser, right? So we create pulses out of it using intensity modulator, and then we do phase encoding using phase modulator connected to a true random number generator, which is giving me say every time a random bit in order to apply a phase of 0 or pi on my optical pulses, which are say 1 nanosecond long, right? Then I attenuate its intensity using variable optical attenuator. I ensure that the average power of the optical pulses is below single photon value, right? Single photon power you can calculate by hc by lambda times t, right? Where t is the pulse duration. C stands for speed of light, H stands for Planck constant, and lambda stands for the wavelength of the optical source, right? Now these optical pulses will then go through optical fiber, which could be say hundreds of kilometers for DPS protocol and 150 kilometers for decoy DPS protocol, right? In decoy DPS, I will be sending two kind of optical pulses, one signal pulse with higher mean photon number, other decoy pulse with lower mean photon number, right? Then I say mean photon number, usually for signal we keep somewhere around 0.8 and for decoy we keep somewhere around 0.2, right? Now these optical pulses are then received at Bob station. They will undergo delay line interferometer where they undergoes self interference, right? And depending upon whether the phase difference between two optical pulses is 0 or pi, it will hit either single photon detector which is connected to direct path or single photon detector which is connected to a longer path, right? Now I will record the time of detection using a time to digital converter, and then I will be doing all the post-processing stages that were mentioned under QKD stages, and then I will come up with symmetric keys. Right? Now, as I increase the mean photon number of signal pulse, there's a finite probability to have multi-photon pulses. Multi-photon pulses provide no security. They are vulnerable to photon number splitting attack because what an adversary can do, adversary can come at very close to the Alice exit. It can perform some kind of quantum wiretap uh, attack where it will keep one photon out of the multi-photon in an optical pulse at its station. Another it will send through a through a link where there's no loss, right? And then whatever Bob will detect, adversary will also have similar setup, and that adversary will get the same key as Bob, and then there is no security, right? So one has to provide security against such attack in their QKD offering, and that can be done using decoy-based approaches. That is what we are doing. Our system generates secure key only if, say, yield corresponding to decoy and signal matches, as well as Q-bar of signal is below the threshold value. Right? Okay. Now, quantum secure direct communication is another way of doing secure communication without generating keys at first place. So there's a forward channel as well as a backward channel. First, Alice sent those weak coherent pulses through a forward channel. Bob received some of them, say 2%, 98% it will use for doing secure communication, where it will be modifying the phase values depending upon the message which it wants to send, right? Suppose it wants to send a bit 0, then it will not do any modification on the upcoming optical pulses phase. If it want to send the message 1, it will change the phase by pi, and then it will resend these optical pulses to Alice's station, where Alice will perform measurement, and based on the outcome and whatever Alice has sent, Alice will determine what Bob wanted to send. That is somewhat described in this particular table. It is very easy to follow. So Alice is sending some input. 0 corresponds to, say, horizontal polarization. In polarization degree of freedom, it is relatively easy to follow. We have done same for, say, differential phase, but yeah, for polarization it is easy to follow. That's why I kept that table. 0 corresponds to rectilinear polarization, plus corresponds to diagonal, minus corresponds to anti-diagonal, 1 corresponds to vertical polarization. So this is Alice input, this is Bob message. So wherever Bob message 1 is there, Bob will apply a polarization change by 90 degree, right? So that is what written pi, right? So yeah, so polarization rotation by 90 degree, and you can understand that it is a kind of state flip in a given basis, right? So suppose Alice sent minus, so after applying a polarization shift by 90 degree, it will become 1, it will become plus, right? And similarly for the rest of the cases, right? And then Alice perform measurement on the same basis which it has used for sending the state, because it knows it is at its own end, right? And then Alice will perform, say, where the detection happened in SPDs, right? Whether it happened on SPD 0 or 1, and what is the expected click when there is no modification which was done at Bob, right? Now Alice will observe the actual click versus expected click in order to determine its interpretation of Bob message. And here you can see the last row is same as whatever Bob message wanted to send in second row. So this is quantum secure direct communication. And now why chakra and why point to multi-point QKD, right? So when we want to scale QKD technology across, say, Indian subcontinent, then doing it in a point-to-point manner is not feasible because it is not cost-effective. Plus, we will require a lot more number of node in order to connect the entire, say, Indian subcontinent. So what is the way forward? Way forward is to come up with a topography which is cost-effective and which can serve as point-to-multipoint. So single photon detector is the costliest element in a quantum key distribution node. And that's why we kept a single Bob station and connected it with multiple Alice station, right? So it generates QKD keys in a time division multiplexing way. So first spoke one will establish a connection with the hub station, will be generating keys, and then spoke two will form a connection with the hub because they are connected with optical switches. So one at a time, these spoke will establish a connection, and they will be generating keys for say 5-10 minutes, right? This is Simulink block diagram. So we also performed MATLAB and Simulink simulation, right, of such a topography. So it is coming from there. And that is the idea. Take multiple chakra subnode and connect them using trusted node in order to provide, say, key exchange between any node, right? So that's how we can cover entire Indian subcontinent. It is live. This is the actual connection diagram with respect to optical fiber and IP addresses between hub and different spoke. And this is the result slide where you can see that actually deployed fiber of 100 kilometer is giving more loss. In lab, it gives a loss of say 20 dB. In field, it is giving a loss of 28 dB. The final generated secure key is 3.2 kbps, and the Kuber value is 3.66 is what we observe. Same for other spoke and whatever, say, the distance of the fiber through which it is connected to the hub station. Okay. We took care of implementation security at each stage. Our boxes are tamper-proof. Our boxes follow the island architecture so that any advancement in any of the component which takes place in upcoming year, we will be able to upgrade our boxes by replacing that particular node, right? We have alarms, we have provide fingerprint access to the UI to say admin and crypto officers. All that is taken care because these technology is created with a decent collaboration with our Indian Defense Forces. So they provided very good their part of the knowledge how a security product like what functionality it should have, right? So we integrated that both for Alice and Bob nodes. And now what can be done beyond QKD, right? So when we are creating a network at such a scale, then that network should not only offer, say, key distribution, right? It should do much more on top of it. And that is the promise I made at the start of this session also, that I will cover a distributed quantum computing algorithm also, right? So I'll take an example of chakra only and example what like beyond QKD what we can do. So we are doing a multi-party computation task where the task is to determine addition of the private data which is there at say Alice 1 to Alice 5. These Alices want to determine say summation of their private data without announcing it, right? And how they can do it using multi-party computation. There are several algorithms classically, but they offer computational security only. With QKD keys we can offer information theoretic security for the same task. So task is simple. Alice 1 to Alice 5 is having, say, secure, say, having private data, small a1 to a5, and they want to determine its addition without announcing or exchanging a1 to a small a1 to a5 with any of these Alices. So what they will do, also these Alices are having pairwise symmetric key coming out of a QKD link or through tested node exchange. Uh, s- uh, uh, that is denoted by X12. So X12 denotes symmetric key between Alice 1 and Alice 2. X23 denotes symmetric key between Alice 2 and 3, right? So in step 2, Alice 1 compute capital A1 by mixing its private data A1, small a1, with the symmetric key between, say, Alice 1 and 2, and like so they are Alice 1 is computing this algebraic equation, which is addition and subtraction of the symmetric key between node 1, 2 and node 5 and 1, right? So it is determining capital A1. Similarly, Alice 2 to Alice 5 is determining capital A2 to A5, which is our algebraic expression written over here. Here we are taking care of the algebraic expression is chosen in such a manner that all the so at the end, this is random in nature because you are mixing some deterministic data with respect to some random keys. So output is random, right? The algebraic expression is chosen in such a way that all these key material will get destructively cancelled at the end. And addition of capital A1 to A5, which is random in nature, is basically the addition of small a1 to a5, and that is what the task of addition in multi-party computation done using QKD keys. And once you can do addition and, say, multiplication, then you can do any kind of mathematical manipulation, and that is what is possible using a quantum key distribution network. So these QKD keys can be used for performing distributed privacy preserving computation. That is what one task and algorithm I thought of capturing for the audience which is more interested on quantum computing aspect of it. Right? So with that, I would like to end my session and open for any follow-up discussion. Thank you so much.
Thank you, sir. Thank you, Dr. Shashank Gupta, for that very interesting session. I
Yeah.
hope the participants would have got really very new insights into what is the quantum QKD distribution and the various protocols that you had discussed. The participants, if you have any doubt, you can unmute and you can ask.
Right. Yeah, I
Also,
can
there's
go to the
yeah,
slide.
yes.
Yeah.
Yes, so this slide is the last slide.
Yeah.
Yes, sir. Am I audible? Am I audible?
Yeah,
Hello.
you are audible. Please go ahead.
Sir, right now you're talking about this is sum of linear equation that should be plus minus cancel, and automatically that we are going to get the data.
Correct.
So if more number of that means persons are involved here, that means we have to go for the more number of linear equations for that purpose, or
So
how we
if
can handle.
more number of spokes are there, which means instead of 5 parties, if we have 7, 10, that many parties, right?
Yes,
Is that the
yes,
question?
yes, sir.
Yeah, so it
Yes, sir.
depends on the topography in a network, right? How these parties who want to perform, say, addition, how they are connected, right? What is the symmetric key they are having with respect to other node? So it is a function. These algebraic expression are function of the way the nodes are connected. So definitely, if say a small A6, A7, and up to say A10 is coming into picture, then one has to determine the algebraic expression such that the symmetric key gets cancelled off, and then the addition of private data is same as the algebraic expression addition. So one has to determine that in such a manner. Yeah.
So that means that the payload, suppose we are talking about the data. So A1 is the data and X1 is the 1, 2 is the symmetry key with respect to LS1 and LS2.
Correct.
Similarly, X51 is the symmetry key of LS1 and LS5.
LS5, right?
Is it?
Yeah, that is true.
Okay. Okay.
So
Okay.
here
Okay.
it is
Thank you,
in
sir.
negative, here it is positive. So that's how X51 will get cancelled off, right? And
So,
similarly,
so,
that's
so
how
when it is a digital type of data, since it is equation type of data, so that's okay. The plus minus is cancelled. So whenever it is going to be digital, that means
yeah.
any
So
extra
it,
operation or some that can be happen also. Or what?
of course, of course. So all this expression, whatever I written over here, right? So everything will
Yes, sir.
follow in finite fields also, right? So that mod 2 logic will work over here also. So finite field also it will hold good.
Okay, 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 sir. Thank you.
Any other doubts from any of the participants? Also, thank you, sir, for this very informative session. And you have really given us a quantum of information, right? A huge quantum of information.
Right.
And on behalf of the management of KCG College of Technology and the organizing team of this 6 days online FDP sponsored by AICTE through the ATAL Training Academy, we extend a heartfelt thanks to Dr. Sashank Gupta for sharing this huge resource of knowledge to all our participants. Thank you once again, sir, and hoping to collaborate with you and interacting with you in the future sessions also. Thank you.
Yeah, definitely, ma'am. And I'll be sharing the PDF version of the presentation with you, and then you can
Yes,
share it with the participants.
yes, because all the participants are requesting for the PDF also. That will be so kind of you, sir. Thank
Yeah,
you.
I'll share it. Okay, thank you so much. Have a wonderful FDP going forward.
Thank you, sir. Thank you, sir. For the participant, we have the session at the same timing starting tomorrow at 6 o'clock. So I'm signing off for now. And thank you for all your active participation. We have still 90 participants online. Thank you so much. And those who have not yet filled the attendance and the feedback link, kindly fill that also. Thank you.
Ma'am, there is only one feedback form and one attendance link form for the 2 sessions.